Welcome to pressure. So, we're going to be talking about gases. Now, a gas is one of our four phases of matter: solid, liquid, gas, plasma, and it has an indefinite volume and an indefinite shape. That means indefinite means that we can change the volume, we can change the shape. The gas takes on the shape of and volume of our container. It expands to fill all the space available. This is different than, say, a solid, which has a definite shape and a definite volume. It won't expand to fill the available space, and it won't flow to take on the shape of the container. A liquid has a definite volume. It only occupies so much space, but it has an indefinite shape. It will take on the shape of the container that it's in. If you pour it into a different container, it will take on the shape of that new container. So that's a gas. A vapor is the gaseous state of a substance above a liquid or solid. So these are the molecules in the gas phase that are below the boiling point or the melting point. So a solid or a liquid always has some vapor pressure above it. There's always some molecules in the gas phase above that solid or liquid. But so if we have water above 100 degrees Celsius, we have a gas. If we have water below 100 degrees Celsius at 1 atmosphere, we have a liquid phase, and there's some vapor above it. Most of the molecules are in the liquid phase, but there are some in the vapor phase above. So, pressure, which we symbolize either as a lowercase p or an uppercase p. I usually use an uppercase p. Zumdahl uses a lowercase p most of the time. So pressure P is the force F divided by the area A to which the force is applied. So if we take some weight and we set it on a table, let's say, the area to which that weight is applying its force, so the size of the bottom of the weight. Now the weight is, remember, being pulled down by the force of gravity. So that force that's being applied is the force of gravity pulling down on the object. So that's the F there. The A is the area of the bottom of the weight, or the area on the table that the weight is occupying. That's the pressure. So if the weight has a larger area, so it's a wider weight, the pressure being exerted on the table is lower because the area that force is being applied to is larger. If assuming that the weight, the force is the same. But if we make the cross-sectional area smaller, then the pressure is higher. So as we lower that area, the pressure gets higher and higher, and at some point, if we get it down to a point, it may be strong enough to gouge a hole in the table. So that's with a physical object, a weight. But we have the same sort of thing if we have a gas in a cylinder. We have some cross-sectional area. We've basically just taken this and turned it sideways. Now only the force is not due to, or not necessarily due to weight of some mass, but now it's the gas molecules as they move around, they bombard the walls of the container that they're in, and that exerts some force. It's a very tiny force for every molecule that strikes the wall, but we have many, many molecules, so that force adds up over some area, the area that the wall occupies. So what this means is that the greater the force that's being applied, the greater the pressure is, and the larger the area is, the lower the pressure is. So the force applied to the area arises from the collisions of our gas molecule with the wall. Right? We have our gas molecules constantly moving around. And for every one of those molecules, in order for it to change direction, it has to exert a force on the wall exerts a force back on it. So the wall sees a force, the molecule sees a force, and then goes bouncing off in some direction. So the collisions of gas molecules in a normal sample of gas are so numerous that the force is essentially constant. It doesn't change with time. Now, if we were to measure that force really, really accurately and precisely, then yes, the magnitude of that force would change with time. But the collisions are so numerous that we can't measure anywhere near that accurately. We have many, many molecules moving around. So essentially the pressure is basically constant. So our force is measured in newtons, capital M, N, and the area is measured in square meters, m squared, meters squared. So remember that the SI unit of pressure is the Pascal, which then needs to be equal to a Newton over a meter squared. So 1 Pascal is defined as 1 Newton per meter squared. Note that also 1 atmosphere is equal to 101,326 pascals exactly, which is equal to 760 torr exactly, or 760 millimeters of mercury. All of these are exact. So if we now have two gases separated by a wall, by a movable wall, so we have one gas over here, another gas over there, and this wall in between we can move. It's a piston. So the gas with the higher pressure, in this case the one on the left, will tend to compress the gas with the lower pressure. So the piston will move to the right, and the high pressure gas will expand, which will lower its pressure. That will also cause the lower pressure gas to rise until they have equal pressures, and then there's no expansion or compression of either one anymore. So it occurs until the expansion occurs until the pressures of the two gases are equal. And when the two pressures are equal, the wall won't move anymore, the piston doesn't move, and our system is in a state of mechanical equilibrium. Mechanical equilibrium meaning that the equilibrium meaning that nothing is essentially changing over time, and mechanical equilibrium meaning that wall isn't going to move mechanically anymore. So the way that we measure pressure is with the barometer, and the original design by Torricelli, which is where the unit of torr comes from, the first 4 letters of his name. He was a student of Galileo. So he invented a tube of mercury that was sealed at the top. He had a vacuum up there, and he pulled that glass tube up above the surface of mercury. Now the air pressure being exerted down on the outside pushed some of the mercury up inside that glass tube. And what he found was that as he lifted this tube up, he could get the mercury to rise around 29.92 inches. He could get it to rise 760 millimeters at sea level on a normal day. And so 760 millimeters of mercury is the normal atmospheric pressure. Now, atmospheric pressure changes with weather conditions. Some days it's a little less, some days it's a little more. And as we change from sea level, if we go above sea level, then the pressure drops. If we go below sea level, then the pressure rises. And so, but that's an average value, so this 29.92 is around 1 atmosphere. It's around the height that the mercury would rise in a tube. But mercury is rather toxic, and so we generally want to avoid having large pools of mercury like this open to the air. So a somewhat more advanced, somewhat safer barometer has the shape of a U like this. We still have a vacuum at this end, only now instead of having a giant pool of mercury down at the bottom that we can breathe in and kill ourselves with, we have a tube, and one end of the tube is open. We still have some of the mercury able to get out this end of the tube, so it's still not totally safe, but it's a lot better than having a giant puddle of mercury there. And so the way that this is measured is with a height difference. As the pressure on this side is increased, that presses down on this side, which means that this left side moves up. And now we have a height difference from the left to the right side. Now, as this side moves up, this side has to move down because there's a fixed amount of mercury in there. And so we measure a height difference, and again, it'll be 29.92 inches of mercury at sea level on a standard day. So modern barometers, the ones that we generally use now, are usually electronic, and they have moved away from using mercury because of the safety hazard involved. So that was pressure and how to measure it.